Okay, I think it's time, so let's get started. So today is the exam 3 review, and the exam 3 is chapter 6, 7, 8, 9. I think there was one question asked me last class if the exam is cumulative or not. No, none of the exam, our 3 exam is cumulative, but you should realize that, well, say if you don't know how to calculate the normal stress caused by bending, if you don't know how to do the shear force bending moment diagram in the previous chapter, there's no way you can solve the problem here, right? So it's not accumulative, but you need to understand the previous chapter to solve the problem in these 4 chapters. So if there's still any problem like shear force bending moment diagram or how to calculate normal stress kind of thing, check your previous lecture notes or previous class recording. So for the horizontal shear stress in the beam, the basic equation we learned in this section was the horizontal shear force is equal to the internal shear force times the first moment area of the cross section, moment inertia of the whole of the entire cross section, and distance. So this is a basic equation, and of course, the most confusing part for most students was the Q, how to calculate Q. So we derived in class Q equal to the distance between the centroid of the cross section and the neutral surface of the entire cross section times the area of the cross section. So if you know how to find the Q, you just plug in and you can calculate everything. So of course, the most direct question asked was how to calculate this horizontal shear force. And I think we have, so for example, determine the shear force in each nail. So in this problem, the delta x is given 25, the geometry they are given, and also, so we know the I, we know the Q, and internal shear force is also given. So basically, we use this equation directly and calculate the shear force. And of course, for the shear force carried by the nail, it is the shear force generated here, right? So as I said in the class, for this type of problem, when we consider Q, we imagine that, okay, we separate this entire cross section into 2 parts through this cutting surface. Now we have either this area or the rest part. So you can calculate Q from either part, but you should also realize that, okay, the top part and the bottom part, the difference is actually a symmetric web. So if you calculate this part separately, the Q of this one is 0. So that's why it proved that why we can either use this one or use this one for calculating the Q. And of course, in the exam, you always want to find the most time-saving part. If you use this part to calculate, of course, you take more time. So this is the Q for this one. And same thing, I think the one of the previous quiz problem, check if it's safe. But of course, we are comparing the shear force generated here with the capability of the bolt. So it has the allowable shearing stress and it has the radius. So we want the delta H generated in the on this cutting surface is smaller than the allowable shear force can be carried by this fastener, which is stress times the cross-section area of the nail, right? So this is the same type of problem. And I think in the longitudinal shear force, it is the same. Determine the shearing force. So as I said, we do not really to like treat this longitudinal shear and horizontal shear everything differently. The best way is just look at them at the same problem. So for example, in this situation, now this becomes a cutting surface. That is on this cutting surface is a shear force carried by the nail, and I think the allowable is given. Oh, it's calculating shear force. No, this is not comparing allowable. And so this is pretty much about the calculating the shear force. And of course, as I said, for this question, we can also ask if it's a design problem, we can ask what is the spacing or what is the maximum force can be applied. So let's say we give the allowable horizontal shear force, we give the cross-section geometry, we give the spacing or delta x, and ask what is the maximum shear force can be applied. So same equation, different way to ask a question. So you can see determine the largest possible, oh, sorry, not this one, sorry. Here, largest allowable vertical shear in the beam. So that is, this one is ask you what is V here. And of course, it gives allowable shear force in each nail is 75 pounds. And also we have this one, the largest permissible vertical shear force, same problem. And we have determine the largest vertical shear. So I would say these are the same problem here. Everything else are given. We need to calculate the V, the internal shear force, or the largest shear force can be applied, the same thing. And of course, the third type of question is asking the delta x. So let's say we put nail along the beam and we ask, okay, what is the smallest, what is the largest spacing can we need to use so that the structure will not fail. So it basically means all the rest are given, how to calculate delta x. So for this one, we have determine the largest permissible spacing S. S is a delta x in the equation. And we have I think this is the homework problem, spacing S and S prime. So as you can see that we practice this type of problem a lot in the in class, the example problem and homework. So I think if you understand all these problems, it definitely is good enough. You do not need to practice, like look for extra problem to practice. And as I said, the most important part is to find out the Q, so the corresponding A. So if we put all of this together, I hope it can help you better understand. So for this one, the nail, this is the horizontal shear force generated and carried by the nail. And same thing here. So if we want to consider one nail, this is area we need to consider for the Q. And the same thing here, this is a cutting surface, and this is a Q we need to use. This is the area we need to use for calculating Q. And here, if we consider one nail again, but if you put like two cross-section of nails, and then you can use this one. It's the same thing in the end, right? And for this one, of course, if you consider one nail, now this is a Q for this area for calculating Q, and same thing here, one nail. And for this one, this is the cutting surface. Horizontal shear force generated on this surface is carried by the nail, and this is the area for calculating Q. And if you put nail in this way, now this is a cutting surface, right? And this is the area we use to calculate Q. Of course, we can use the rest part, but it should be the same. And for this one, same thing. If we consider the nail here on the side, then this is a cutting surface, and this is the area for calculating Q. And if we consider the nail on the top, and then this is the cutting surface, and horizontal shear force generated on this surface is carried by the nails. So now this part is the area we use to calculate Q. And of course, I think a simpler way is to use this one. I think the solution I used this one because we already have this part and this part. I just add this one together. So in terms of the calculation, I think possibly is the same workload as you use this one. So well, you can make your decision during the exam. So this is for horizontal shear force or longitudinal shear force, it doesn't matter. So any question for this part? Okay, so for chapter 6, the second very important topic is the shear stress. So the equation, the general equation we used is the VQ of IT. Right, we derive this one, and when we say average, it means average in this direction. And we also showed why we can kind of consider this is a constant in this direction. I show you a table when this is never enough. So this is the basic equation, VQ of IT. We need to know the internal shear force point at the point that we want to calculate this shear stress. We need to know, again, the Q and moment inertia of the entire cross-section and the thickness at a point where we need to calculate the shear stress. So this is a general equation for calculating the shear stress. And of course, we also derive the equation for two special situations. One is the rectangular shear, rectangular cross-section. And we had, just here on my iPad. So derived from this equation, we plug in like everything, what is the Q, what V, I, T, everything. And in the end, we have the tau equal to V over A 1 y squared. This quadratic function, right? So it means that, okay, this shear stress, it quadratic change in the y direction is a quadratic function of y, so it quadratic change in the y direction, and at plus c and minus c, which is top surface or bottom surface, we plug in this one equal to 0, because this one equal to 0, right? And its maximum at neutral surface when c is equal to 0. So now this part is well, this part is 0. So now this one becomes the maximum shear stress at neutral surface. So I can write tau max equal to average, the internal shear force divided by area, which is average shear stress we calculate at the very beginning of semester, and it's 1.5 times average. So this is the maximum shear stress for rectangular cross section. And of course, the A here is equal to, if we label in this way, is equal to 2BC. So this is one special case for the rectangular cross section. Is derived directly from this one, and everything you calculate here, if you use this equation and if you use this equation, the result should be exactly the same. I think I showed in one homework solution. I used this equation and I also use this equation. In the end, the answer is the same because this one is derived from this equation. And this one is a little different because it's not like exactly derived from this general equation, but we, let's say we do some test and we find out, okay, this is the distribution of the shear stress if it's I-beam. And then we had an approximation. Equation, which is tau max, we consider is here, or we consider this is a straight line, and all the shear stress in this range should be equal to V over A web. And this is the area of A web. So for the I-beam, this is a simple way to calculate. So to calculate the maximum shear stress, also the shear stress in this region. And of course, this is approximation, is a simplified way to calculate shear stress. You can use this equation if you have enough time. If you want to like take extra effort to calculate shear stress, you can use this equation, and the calculated result from this equation will not be exactly the same as this one because this is just approximation, but it should be very close. These are two special cases for the specific cross-section geometry. And we had a example problem in the class. So I think this is directly use this one and calculate design acceptable or not. So it gives a allowable shear stress. So this is a this is the direct application of this equation. So you find out what's the V and you can calculate what's A, and that is maximum shear stress, and you compare with allowable shear stress. And the same thing here, this is the direct application of this one. If it's I-beam, so this is I-beam here, shear stress, right? So in the homework, we had a more complicated problem. So for this one, of course, based on the loading condition, you know what is the internal shear force at the end cross section, and you need to calculate the A shear stress at A and B. So now for this one, we need to use the original equation now. So we need to use, let's use different color, this equation. And of course, in this equation, we need to find out what is Q. So let's say determine the shear stress at A. We consider this is the area we use to calculate Q, because let's imagine we separated entire cross section into two parts by cutting through A. So we can either use this one, or we can use all the rest part, right? And of course, this part is easier to calculate. So this is how to calculate shear stress at point A. And for calculating shear stress at point B, same thing. Let's cut through point B. And now we separate the entire crossing into two parts. We choose this one to calculate. You can use the rest part, the same thing. So we use the original equation, tau equal to VQ of IT. V is given, Q I just talked about how to calculate it. And I, entire cross-section, the moment inertia of entire cross-section, we already practiced many times. And T, the thickness, is the thickness here. And we also had this one. So I think, is this the homework or exam problem? So this is the same thing, cut section and end. So by given loading condition, we know what is the internal shear force at its point, and the largest shear stress in the section and shear stress at point A. So the largest shear stress is always at the neutral surface of the entire cross section. So this one is symmetric. So this is the neutral surface of the entire cross section, and at this location, we have the largest shear stress. So it basically means that, okay, how to calculate the Q for this part. So check my solution. I think I put a lot of effort to make the solution. Read that in detail. If you have any question or any part you're confused, ask me. And part B is the shear stress at point A. And shear stress at point A, then we use this part to calculate Q, right? We separate the entire cross-section through this cutting surface, and we use this part to calculate Q. So we had a quiz problem that is a simplified version of this question, the largest shear stress. Now I simplify the cross-section as a T shape, and everything else I think is the same, and calculating the maximum shear stress. So as I said, you find the neutral surface of the entire cross-section, and you can either use the top part or the bottom part to calculate Q. And then I think the solution, I use the bottom part because bottom part is easier to calculate Q. So we know the V based on this one. We know the Q based on this area. We know the I, moment inertia, based on this T shape. You know how to calculate the moment inertia of T shape. And T is this dimension, right? So this is so the quiz problem is a simplified version of this problem. So I think this is pretty much the second type of question in this chapter. And so calculating, first one, calculating horizontal shear force, second one, calculating shear stress. Any question here? So chapter 7 is stress transformation. So basically, let's say we have the static stress for an element that is like two surface parallel to the x direction or any direction. Normally it's parallel to the x direction or perpendicular to x direction. And then we want to find out, okay, if what is the maximum normal stress and shear stress after we rotate the element. So in that situation, we can find the maximum normal stress and the maximum shear stress that will cause the structure to fail. So for the stress transformation, we have two methods. We can use the equation method. We can use Mercicle. If I don't specify which method you have to use, you can use either method you want. If I say, okay, solve this problem using Mercicle or using equation method, then you need to use that method. So a lot of times, you probably already know that in the problem in chapter 8 is combined loading. you in the final step, you need to use this one. So in that situation, well, you use any method you want. So for this one, I already post all the equation you need for the exam 3. So these are given. And I think the part that might cause confusion was the definition of theta. So all these equations are derived based on the theta is from the x to x prime counterclockwise. And you can plug this theta into the equation and you'll get everything correctly. Otherwise, you will mess everything up. And the second one is the sign convention for tau. So let's say when it has a state of stress given here, or like this, should we put positive tau there or should we put negative tau there? So that is the sign convention for using this equation, sign convention for tau xy. So I talked about this in class. For tau xy, we consider we use the second order tensor as the sign convention. So it basically, if it's on the positive surface and in the positive direction, it's positive. So for example, this one is on the positive surface, but in the negative y direction, positive x surface, but negative y direction. So this one, we should put negative 25 into the equation. And for this one, it is on the positive x surface and positive y direction. So positive is positive 40 into the equation. And same thing, all the rest are the same. So these are the two parts we need to be careful. One is the definition of theta. You need to follow this theta definition, otherwise this equation won't work. Second is how do we deal with the sign for the tau xy when we plug into the equation. And of course, a way to help you save time for this calculation is that, okay, let's say it asks what is sigma x, what is the principal stress? Principal stress is, you just calculate sigma x prime, sigma y prime, and tau xy, everything, x prime, y prime. But we talk about a property is the sigma x prime plus sigma y prime equal to sigma x plus sigma y. So if you know this property, basically means that no matter how you rotate the element, the normal stress, the sum of the normal stress on the two planes, they are constant. So to save some time in the exam, if you really want to use the equation method, you can calculate sigma x prime, and then use this one to calculate sigma y prime, right? Then you can save time for using this equation. So that's this all the trick. So the second method is, oh, sorry, this is not principal. So this is rotating any random angle. So angle given, what is sigma x prime, sigma y prime? I think I said something wrong. And now this is the equation for calculating the principal stresses and maximum shear stresses. So again, tau xy sign convention is the same. And you can use this one. If it's plus, is corresponding maximum stress. If it's minus, it's corresponding minimum stresses. And maximum shear stress, you can use this equation. And these are the two equations to calculate in the angle rotation. And I don't think there's like too much thing to say about equation method. The equation method, basically, you just plug in everything into the equation and calculate, and just need to be careful of this. And the second method of the stress transformation is Mohr circle. So basically, if we reorganize the equation we derived in the previous section, and we get this equation. And now this equation, you can see that this is the equation for a circle, and this is a center, the sigma coordinate of the center, and this is a radius, and these are two expressions here. And for this one, I think there are several parts that we need to be careful. The first one is I talked about in class. Whenever there is a shear stress that is rotating the element clockwise, you put it above the sigma axis. Whenever there is a shear stress that rotates the element counterclockwise, you put it below the sigma axis. So this is a convention to construct the Mohr circle. And second one is if we rotate theta p in element, it rotates 2 theta p in the Mohr circle. In the same direction. And once you have this Mohr circle constructed, then you can have what normally we use it to calculate, to find out whatever is maximum, right? Maximum normal stress, maximum shear stress. So now the maximum is equal to sigma average plus radius. Minimum normal stress is equal to sigma average minus radius. And the maximum shear stress is equal to radius. So it basically means we use these two data points. First, from the state of stress of the element, we can put it on the coordinate, the sigma tau coordinate. And let's say this is a 2 data point, and a straight line connecting these 2 data points is the diameter of a circle. So this circle is identified. And once we have this circle, we can find out the center of the circle, and the sigma coordinate of the center is half of the sigma y, sigma x, right? And then from this circle, we can easily see that, okay, now this is where the maximum normal stress located, minimum normal stress located, maximum shear stress, or in terms of magnitude, this is also maximum shear stress. This is equal to radius. And here is equal to the coordinate equal to the coordinate of the center of the hole plus radius. And for the minimum is the center of the hole coordinate, sigma coordinate of center of the hole minus the radius, right? And shear stress is this length. This is radius. So for this one, I think they just changed the direction, change the magnitude, but well, you can see that it's basically the same thing. If you know how to calculate one, you know how to calculate all the others. So there's really no trick here. And this was a quiz problem in the last summer. So again, it's the same thing. I put a red surface here. It basically means that, okay, you need to calculate sigma y, right? We normally consider, okay, we normally put this is the x-axis, this is the y-axis, and everything you calculate on this surface is sigma x prime, tau x y prime, y prime. And if I say you only need to calculate the red surface, it basically means that you calculate sigma y prime, right? And tau x prime, y prime. So this is the 2 methods about the stress transformation, equation method, Mohr circle. You need to know how to use both. So the chapter 8 is about the principal stress. We have the principal stress in the beam and the principal stress or maximum shear stress in the transmission shaft. And section 3 is to put everything together. So I would say that the ultimate goal is section 3. We put everything together, but the first two is just like we take some baby steps. So to understand them separately. So the first one, calculating the principal shear stress in a beam. So for this type of problem, we know that if we apply a force here, of course, when we talk about this type of problem in the beam bending chapter, we only calculate what is the normal stress generated for this force in the bending situation. And then in chapter 6, we calculate, okay, what is the shear stress by this force, by this transverse force, right? And now in this chapter, we combine them together. Okay, we have this force caused by bending, and the bending moment is equal to this force times this distance. And we also have the shear stress caused by this transverse shear. And this is also the internal shear force in the beam. So we now combine these two together, right? And in the chapter 7, we know how to, if we have the normal stress, if we have the shear stress, how do we find out the principal stress, maximum normal stress, minimum normal stress, maximum shear stress? So it's more like combine these together. So of course, after we learn this chapter, we need to, when we see this type of problem, we cannot just see it like separate, oh, this is just bending. No, it also has a transverse shear, right? So we always need to consider everything together. So for any force here applied in this way, it causes bending, it causes transverse shear. Bending will generate normal stress in the beam, and the transverse shear will generate shear stress in the beam. And we calculate those separately, and then we put in the element, okay, what is normal stress generated at a specific point? What is the shear stress generated because of this transverse shear? And then using this one, we calculate the principal stresses and maximum shear stress. So you can see the question type, it has, if the normal stress satisfy the design specification. So basically I have the allowable, and then this is allowable here, and you need to calculate the maximum normal stress in the beam and compare it with this allowable normal stress. And for this one, same thing. It asks you to calculate the principal stresses at different point. Maximum value of normal stress, sigma m, and at A and at B. No, is it? Oh yeah, it's the either the top surface or the point, junction point of the flange and web, and compare them with allowable stress and decide if the structure is safe or not. So basically you need to calculate the maximum stress in the structure. And this is a quiz problem. It's our quiz 6. So I would say that, well, if you check this too, it's the same problem, right? I changed this loading condition to this one. Well, it should be the same thing. And I ask you to calculate principal stress and maximum shear stress at point A. So this point A is same as the junction of flange and web. Right. And the maximum value of principal stress is principal stress, and of course maximum shear stress. You just go one step ahead. You R, the radius of the Mohr circle, is the maximum shear stress. So this one and this one, this homework problem and this quiz problem is the same problem. I just take part of this one and make it a quiz. So if you felt that the quiz 6 was like extremely difficult, maybe you need to check your homework and exam problem in class. So this is a principal stresses in the beam. Again, we need to consider bending and transverse shear. And when we talk about the shaft, we have we added torsion, right? So as you can see here, now this P we generate torque, and this torque we generate a shear stress in the shaft. And the same thing here, it generates the torque in the beam and it has shear stress. And at the same time, for this force applied, we can consider, okay, it generates torque, T, and it also, we can see this P here as a torque plus this force applied to the beam. So this force, it can generate transverse shear, but for this section, because we want to separate everything, so we ignore the transverse shear, and it generates bending. Same thing here. If whenever there's a force applied to the beam that is perpendicular to the axial direction, or it has a component that is perpendicular to the axial direction, it will cause the bending. So for this section, since we ignore the transverse shear, so it basically is a combination of torsion and bending. Same thing here, it has bending in this plane and also bending in this plane, and then combine it with the torque. So this is the second section of this chapter. And now we combine everything together. Now this is section 3, which is, well, I personally think this is the most important topic of the whole semester. But somehow I mistakenly skipped this part in the last summer. So I already posted the previous exam. You cannot see anything that related to this this part, but this is very important topic. So don't be surprised if you see it in the exam. So for this one, it's basically we have tension, compression, torsion, bending, transverse shear combined together. So the most important thing is that for the given force applied, you need to do the analysis yourself. Okay, what kind of the deformation mode it causes, and what kind of stress it causes. So let's do it one by one. Since this is a very important topic, I want to spend more time here. For this force here, of course, it's easier if we resolve into the X component and the Y component, right? So for the force P, we can consider, this P times this one, it will generate a bending moment about the Z-axis, which is into the plane or outer plane direction, about the axis into the plane or outer plane direction. So this one, you can consider it causes a bending, and it also causes tension, right? So tension, sigma stress, normal stress, and bending. And for the Y component, well, for this one, it will cause this force times this moment arm is a bending. It is also a bending moment about the Z-axis. That's why I put these two together, right? And also it will cause the transverse shear. So these are the tension, bending, transverse shear caused by these two forces. And for the stress at each specific point, the stress at that point might be 0. So for one step ahead, we need to know how is the stress distributed. So this is the detailed information in the previous chapter. If you are confused about this one, you need to check the previous lecture notes. So for the normal stress generated by the tension compression is uniformly distributed over the entire cross-section. Is the bending stress positive or negative? Bending stress positive or negative? I will talk about this later. So let's start from the normal stress. Normal stress, so this is uniform distributed. So no matter what point we are talking about, we always have normal stress and it's always a constant. So this part is easy. Tension, compression, normal stress, constant entire cross-section. The problem is the bending. So bending is positive or negative. It's determined by the bending moment. Well, let's say, I think I calculated the bending moment for this one. You can check the detailed solution later. The combined bending moment caused by this V and P in the end is, I think it's in this direction. The bending moment, let's say that it's in this direction. So if the bending moment is in this direction, then is the bending stress positive or negative? It depends on which point we are talking about. So if we have a bending moment in this direction, this is how the normal stress distributed, right? It is positive at the bottom surface and negative at the top surface, 0 at neutral surface. Is this clear? Okay, great. And also let's make it like more standard way. We're not saying bending stress is normal stress caused by bending. So it's normal stress sigma caused by bending. And of course, if let's say if we have a bending moment we calculate in the end, it's bending moment in this direction, then I'm really horrible at this. Now, this is how the stress distributed. So if the bending moment is in this direction, then on top surface or point A, it is positive. Neutral surface, point B, it is 0. What is happening here? And at the bottom surface, point C, it is negative. Compression on top is compression top negative, tension positive. Yes, so for the sign convention for tension compression is always the same. Tension, tensile force, tensile normal stress, the internal normal force is always positive when in tension and negative when it's compression. So this one, there's no confused part. So now this is let's remove, make it less confusing. Remove this one. Normal stress generated by bending. And the third one is a shear stress generated by the transverse shear force. So this one, as I reviewed in the chapter 6, for this is a rectangular cross section, of course, is coordinate exchange. I show you the equation, and is 0 and top and bottom. That's why at point A and point C, there's no shear stress. But at point B, it has a maximum. So for this problem, for calculating point A, we have normal stress generated by tension, normal stress generated by bending, no shear stress. At point B, we have normal stress generated by bending, shear stress generated by transverse shear. And at point C, we have the normal stress generated by tension and normal stress generated by bending. So of course, when they ask about normal stress, you always add these two together, right? Superposition. So shear stress, we can also add together. And of course, when there's, I will show you later, when there is a torsion, shear stress generated by torsion and the shear stress generated by transverse shear, they are in different direction. You need to put a sign there. So it's either add or minus, plus or minus. So I think this is the most important part for this type of problem, because if you already check the solution in the textbook, like the example problem, the homework solution, well, I made a solution myself, but if you check the standard solution, you can check it online. It just gives you, okay, the sigma equal to something plus something plus something, tau equal to something plus something plus something. Well, the problem is that how do I know, right? If you're not clear with this part, how do I know which component plus which component plus which? It's going to be a whole mess. And you may miss some part, or sometimes you may mistakenly add some extra part that is not generated there. So I would say you are clear about this part first, and then you can say, okay, sigma is these two together, and for C point, these two terms together, and the shear stress for point B is only one term. So you need to be very clear about this one. And this is also the example problem in the class. And for this one, I already did this part, so it might be a little bit more clear than the one I did in class. So for this one, it's a compression. It's a pure compression. There's nothing else generated by this force. So it's compression, uniform distributed force. So it doesn't depend on which point, it's always there. 0.5, this force, as I said, when the force is applied this way, it causes bending. About z-axis is bent in this way, right? So it's about z-axis, bending moment about z-axis. So we have the mg, and it causes the transverse shear in the y direction. Let's rotate. It causes transverse shear in the y direction, vy. So the bending moment will generate the normal stress, and this normal stress, of course, H is on the top surface. So yes, it has normal stress. Transverse shear, it has, for the transverse shear force, it will generate shear stress. But this shear stress, because it is 0 at the top surface and H is at the top surface, so there's no shear stress here. And for this force, 2.5, again, this is the this is the moment arm. There's a bending moment about y-axis. It bends in this way, right? So we have my, and we have the transverse shear force in this z direction. We have the vz, and now we can check. Now H is at the neutral surface of this cross section. Now H is the midpoint if we consider it's bending in this way, right? So H is the neutral surface, the stress, normal stress is 0, right? And for shear stress, well, now if you consider neutral surface, shear stress is maximum. So we have the shear stress. So these are the, we consider the force applied and the specific point in this problem is H here. So now when we consider normal stress, when we consider these two components, compression and bending about z-axis, when we talk about when we calculate the shear stress, only one component. And now we can calculate, okay, for this element, for this, it have on this H, it has the normal stress, you calculate it, it has shear stress, you calculate it. And then you can calculate what is the principal stress and the maximum shear stress. So back to the original equation in chapter 7, right? From this one to this one. So again, be very clear about this part. And this one is the one that has the torsion involved. So now, well, just by imagine this force applied, let's say if we apply a force like this, you can imagine that it can rotate this bar AB, right, in this way. So of course, this force P2, it will generate a torsion. And this torsion T, we talk about tau equal TC over J. We have shear stress. And this shear stress, let's put it here, I think. We said that the shear stress distribution along the at the entire cross section, it looks like this. It's linear change and maximum at the outer surface and 0 in the center. So this is a shear stress distribution. And at, well, let's say no matter h, k, it always the maximum, right? It's just different direction. At point h, it is in this direction. At point k is in this direction, but it's always maximum because it is outer surface. So the equation TC over J, C is outer radius. And this is the new thing for this problem, torsion. And of course, this P2, it can, if you moved here, then it can bend the moment, bend the beam like this, right? So it's a bending moment about z-axis, mz, and of course, it has the transverse shear in the y direction, y. And bending moment, it generates normal stress. And let's say if we put a force and bend about z-axis, the k point is the neutral surface. So the normal stress is 0 at the neutral surface. And for the shear stress, neutral surface is maximum, non-zero. And so this is everything about P2. And back to P1, of course, this one, this force times this moment arm will generate a bending moment about y-axis, so it will bend in this way, right? The beam will bend in this way. So we have the my, and if we move the P1 here, well, basically P1 is equal to, I move the force here plus the bending moment, right? And so this force, it will generate compression. Compression, normal stress, compressive stress, constant everywhere. No matter what point we're talking about, it always have normal stress. Bending moment, now when we bend in about the y-axis, bend in this way, this becomes the top surface, right? So it has maximum positive normal stress. So now if we're clear about all this part, so we know that normal stress, we have two components, shear stress with two components. We add this add this together. So normal stress, shear stress, and then we can calculate the principal stress and maximum shear stress. So this is when there is torsion involved for this type of problem. And these are the homework problem, same thing. We separate this three force and I put it here. And this one, this force will generate bending, torsion, transverse shear, right? Because if you imagine if you have an L-shaped structure and you put a force in this direction, in the y direction, it will rotate the L-shaped structure in this way. So there's a torsion here. And for this one, it's pure compression. Any question here? I hope that put all the problem together is easier for you to understand. And once you understand all this part, the rest part is just pure calculation. So it won't be difficult for the pure calculation part. But you need to be very clear of this. And last chapter is deformation of the bending. So for this one, I think we just did, well, there was no new equation, just I don't know what happened. That's right. We use the curvature. Mathematical formula of curvature is dy dx second derivative is equal to the curvature we learned in the chapter 5 is the m of EI, right? Bending moment, internal bending moment divided by Young's modulus times the moment inertia. So this is the curvature equation, and integrate this equation once, you get the slope dy dx. Dy dx is the slope, and integrate that equation again, you get the function of y, which is deflection, and the whole problem is solved. And of course, when you integrate once, you have one constant out. When you integrate twice, we have two constant out. So the unknown constants is something we need to solve. And to solve this unknown constant, we need to use the boundary condition. So for, let's say, for the first example problem, the two boundary condition can be, let's say, if we define this is x-axis, then it means that at this point, which is x equal to L, the rotation is 0, and the deflection is 0, slope is 0, and the deflection is 0. And this is a clamped or fixed boundary condition. And for so the difference of this one and this one, it basically here it does not allow to rotate, but for this pin joint of roller support, it can rotate, right? So this is the difference. So for this one boundary condition, it has well, this clamped or fixed support, we can write two equations: y equal to 0, dy dx equal to 0 at x equal to L. Or if you define the x direction in this way, then this x equal to 0 depend on what x-axis you want to use. And for this one, since it does not constrain the rotation, so the only boundary condition I can put at point A is, let's say this is the x-axis, then it means x equal to 0, y equal to 0. But we don't know what is the dy dx, the rotational slope here, because it's free to rotate. It can bend like this, right? Sorry, bend like this. Same thing here. So for the two boundary condition, at this point, y equal to 0, at this point, y equal to 0. And for this one, it's a little bit different. So this one, we need to write the equation, bending moment equation on this section, on the AB section and BC section, and integrate this one twice. We have two constant. Integrate this bending moment equation twice. We have two constant. So we have 4 constant, unknown constant we need to solve. Then we need the full boundary condition. And of course, at point A, y equal to 0. At point C, y equal to 0. These are two boundary conditions, two equations we can have. And the extra two equation is that at this point, because we know that, well, no matter how you deforms, the deformation curve should be a smooth curve. So it basically means that, okay, at point B, where the force applied, the deflection we calculated from the left part, from the AB part, should be the same value as the deflection we calculated from the BC part. So y1 should be equal to y2. And same thing, the slope at this point should be the same thing, should be the same when we calculate from the AB section and BC section. So theta 1 equal to theta 2. So these two equation plus one equation here, y equal to 0, y equal to 0 here, we have 4 equations, we have 4 unknowns. We can solve this one. So we know the maximum deflection, we know the y as a function of x. And the maximum deflection basically means dy dx equal to 0, right? And to find the corresponding x, plug back into this equation, that is the maximum deflection. And so this is the statically indeterminate beams. So, oh no, this is not, sorry. This is the homework. This is the statically indeterminate means. So homework is the same. You can check the solution. And for the statically indeterminate means, for this one, there's a redundant support. So redundant support will cause extra unknowns. So for this one, we need 3 equations, right? 3 boundary conditions to solve 3 unknowns. So basically for this one, at point B, y equal to 0. At point B, rotation theta or dy dx equal to 0. So these are 2 equations. At point A, y equal to 0. So these are 3 boundary conditions solve for the 3 unknowns. So we can calculate what is the reaction at A. Because if you write the bending moment about x, it's a function of ay. Ay is unknown. And then you have the C1, C2. So these are 3 unknowns. And you have 3 boundary conditions. Solve the 3 unknowns. And same thing for the homework. Redundant support, right? Actually, these 2, in terms of boundary condition, the same. It just the loading condition is different, but I consider it the same problem. And the superposition method is basically okay because for this one there's no 2 forces combined together. Okay, so superposition method basically means that okay, we have the different force, different loading condition applied on one beam at the same time. So for this one, you can use the original method. So if everything applied at the same time, what is the, let's say for this one, what is the bending moment m as a function of x and m function x in 2 different sections and use the boundary condition we talked about, we solve this problem. So that one can be done. Calculation part, very complicated, but it's doable. I would say it's doable. And a simpler method is that we consider them separately. So we calculate what is the deflection if we only have the bending moment applied. We have the, let's say, y1, theta1 for only bending moment applied. And then now you imagine that if only the force P apply, what is the y1? What is theta1? And in the end, sorry, y2, theta2. And in the end, y equal to y1 plus y2, theta equal to theta1 plus theta2, right? So this is the basic idea of superposition method. So basically, you calculate everything separately and then add them together. So in terms of calculation, what is the same? We consider the uniform distributed force first, calculate everything, and then we consider only P applied, calculate everything, and then add them together. So in terms of calculation, I would say that it may reduce the calculation load by using this superposition method. But the biggest meaning of this part is that at the appendix of the textbook, every textbook of the mechanical materials, there is a table. It shows that, okay, for a cantilever beam, if a force applied to give you the final answer directly, what is the expression of deflection? What is the expression of the rotation? So let's say for this force applied, you find this expression in the table. And for this moment applied, you find out the expression in the table. And then you add them together, and then you're done. So for this semester, I just want to know that there is something like that exists. You can use that after this semester, let's say when you're done with this semester, or when you do, so let's say after you graduate on job, you do not need to like really use hand calculation, but you know that you can use some manual too, and then add them together. So this is the purpose of learning this superposition method. But for this semester, I do not recommend you use this appendix. Use the result from the table directly for any homeworks, quizzes, or exams. That is not allowed. because our goal of this semester is to build a solid foundation. It's not, I'm not teaching you how to check the appendix and use the manual to put the result here. That's not my job. So this is the superposition method. So any question? Any question of any point I talk about in this class, or any question about the exam itself?
What time is our exam?
It's Wednesday from 7 to 9.
Okay, thank you.
You're welcome. Since we have 0 minutes left, I want to put the basic procedure for this one. For this whole chapter, actually. Would there be a question? No, there's no. Just no question like that. So for all the problems in chapter 9 about deflection of the transverse loading, we have basic procedure. Since we have 0 minutes left, we can. The first one is we need to calculate reaction force if necessary. And of course, if it's something that like this, you probably don't need the reaction force. So reaction force is for something, for the problem like this type. So you will need a reaction force. So the first step is calculate, use the global free body diagram and equilibrium equation to calculate reaction force if necessary. So basically the free body diagram of the entire geometry. And then the second one is use the free body diagram and equilibrium equation of the cut section. So this one, we do not need to like write everything, but we need to have a bending moment as a function of x. Basically, we need to know internal bending moment at any point through the whole beam. And then once we have this m as function of x, we can write it as the third step, ei dy dx. So for this equation, we integrate once, we can have the ei dy dx, right? And then we can also integrate again, we can have eiy. So this is the expression for slope or rotation. This is the expression for the deflection. And of course it has, so for this one, it probably has one constant and this one has another constant. And to solve for this unknown constant, we need to apply boundary condition. So, and boundary condition, it depends on what kind of boundary condition. If it's a pin joint or roller support, it basically at that point y equal to 0. If it's a fixed boundary condition, it's y equal to 0 and theta equal to 0. Or if I'm more comfortable with this one, dy dx is equal to 0. It's the same thing. So this is how we apply the boundary condition, depending on the boundary condition type. And one part that if there's a concentrated force applied in the middle, applied on the beam, then we can have the theta 1 equal to theta 2, y1 equal to y2. So this becomes the extra two boundary condition we can use, because we need to have the m on the right part, on the left part and the right part. So we have m1, m2. So we integrate once, we have theta 1, theta 2, and y1, y2. And so now we use this one to solve the unknown. And once we have the unknown are solved, everything is done, right? You have the deflection equation, we have the slope equation. To find the maximum, you put this one equal to 0 and plug in this equation, and you're done. So these are the basic procedure for all the problem in chapter 9. So I think time's up. So good luck on the exam 3. And if you have any question, I'll be in the office hour at 12:30. And go back to the 7.2. 7.2. So here. You're welcome. So if so thank you for coming to class and have a great day.
So how do you know when to split? Pretty much anytime you have a concentrated force on your beam, you're going to be splitting it. You're going to have like a Y1 and a Y2, correct?
Yes.
Okay.
You have to, yes.
Okay, but a distributed load doesn't necessarily need that, correct?
No, distributed load, you can just use one equation.
Okay, awesome. Thank you so much.
You're welcome. Thank you. I'm glad to hear that.
Oh, do we have lecture on Wednesday of any kind?
Nope.
Okay.
I will have office hour.
Okay, awesome. Well, it's been great. Thank you so much.
Scroll down. Scroll down here. There's nothing here. For 2, 3, 4. 2, 3, 4. What is 2, 3, 4? Oh, okay. Sorry. You're welcome. You too. Thank you.